And our next invited speaker is Steele from the London School of Economics, and she is going to talk to us about model selection methods and the use-novelty criterion.
Thank you.
Thank you.
Thanks, Jill, and thanks to Raphael. Pleasure to be here, of course. So, yes, this is based on joint work with my co-author, Charlotte Verndl, but actually our sort of finished joint work is in the past, so I can't say that she would necessarily agree with everything I have to say now. It's more my research for our next joint paper. So there's sort of two themes really that I'm interested in here, right? And the first one is a general interest that I have in the difference between classical and Bayesian inference, right? So inference, the topic is sort of relations between hypotheses and evidence, right? Issues of the extent to which we think some evidence confirms or disconfirms a hypothesis, what we should think about the hypothesis after we've learned some evidence, how confident we should be in hypotheses, that kind of thing. So when I say inference, that's what I mean. Questions about the extent to which we think a hypothesis has been confirmed, or we should have a rising confidence in the hypothesis, right? So, I mean, this classical versus Bayesian distinction has more to do with statistical hypotheses. So, hypotheses that specify chances for things in the world, right? That specify basically a probability distribution over possible events. Now, the other theme is a discussion in the philosophy of science, which is this use-novelty discussion about the status of evidence that's being sort of already used to construct a theory against evidence that is sort of new or novel predictions, right? Now, a lot of that discussion actually concentrates around deterministic hypotheses, where you sort of set up your notion of the hypothesis such that it entails this evidence for sure, right? And so if you observe not that evidence, you know the hypothesis is wrong, right? So, but the interesting connection between these two comes when you extend this idea to indeterministic hypotheses or statistical hypotheses, right? And that hasn't tended to be a focus in the literature, so certain things have been kind of forgotten. But I think the extended case does reveal some interesting things about this first question. So that's the connection. Okay, so I am just going to say a few comments about the first issue, the difference between classical and Bayesian as I see it, right? There's sort of many people have their takes on this distinction between methods of inference, right? I just want to make some comments on that, and then I'm going to basically put it aside for a while and talk about this use-novelty stuff in the philosophy of science literature. So basically, I think the best way to put the distinction is as follows, right? So for the classical or frequentist statistician, inferences about hypotheses H based on evidence E is mediated by the testing procedure, right? So it's actually the testing procedure that, combined with the evidence, tells you how much you should think that H has been confirmed, or what your rising confidence of H is, right? So the testing procedure might be the type of experiment that you're doing. If it's a coin toss experiment, let's say you've decided to toss the coin 100 times to test the hypothesis about the chance of the coin, right? So in this case, this experiment, the fact that you're tossing the coin 100 times is an important component, or it mediates, it's important information in terms of your final assessment of H given the outcome that occurs. I'll give you another example in a second to make that more clear. For the Bayesian, this inference about H based on E depends just on the probabilistic relationship between H and E. Right? So it's only this particular outcome, E and H, that matters. So another way of putting it is, for the Bayesian, you only care about what relationship you posit in your probabilistic model between H and E. It only matters your confidence in H upon finding E. All that matters is E and H. For the classical statistician, if you like, how you found E is also important. Right? It's not just E and versus E with respect to H. It's, well, how did you find E, and was that a reliable method for finding evidence? Is that the sort of method that we would think should give us confidence in H? Right? So just to give it a quick example, although it might not illuminate all of this stuff, but so assume we're not sure what experiment has been run to test a hypothesis H concerning the chance of heads for a coin, right? But we know that the outcome is 6 heads out of 20 tosses, and the last toss was a head. Right? So we don't. What do I mean? We don't know what test was being performed. Well, often people think of tests in terms of the stopping rule that's used. Right? That's just one way that you might define a test in terms of the stopping rule. So this is a different procedure or a different test, a different experiment from this one. Tossing the coin 20 times, right? You can think of the outcome space. It's all the possible sequences with 20 tosses, right? Versus tossing the coin until you just get 6 heads. And that might have been the test that was performed. That's quite a different outcome space. You can have indefinitely many coin tosses in your sequence before you get 6 heads. So the space of possible outcomes for this one looks quite different from the space of possible outcomes for this test, right? And that's effectively why the classical statistician may say different things in those cases. So the Bayesian, for the Bayesian, it doesn't matter which one of these tests was performed. If you're not sure, no one tells you, doesn't matter. We know what the outcome is. We know what probability the hypothesis confers on this outcome. We know their relationship. That's all we need to know. Now we can make our inferences about H. Right? For the classical statistician, it does matter which one of these was performed, right? Because your inference about H is based on E is mediated by the properties of the whole test, right? And think they have different outcome spaces. So the properties of this test in terms of its accuracy, long-run accuracy or average accuracy, or error probabilities, right? In this case, differ for different tests, and that's important. So again, I'm just repeating myself in different ways. Inference is tied to long-run properties of the test. So how often does this test get it wrong, get the wrong answer in the case where H is actually true or in the case where H is actually false? That kind of thing, right? Or in the case of estimators, sort of how on average, how inaccurate is this estimator? Right? So inference in a single case depends not just on what happened, but what could have happened and what would have been inferred in other circumstances, right? Because these other circumstances define the properties of the test as a whole, and that's important. For the Bayesian, inference just depends on what happens in the single case. Right? It doesn't matter, if we got 6 heads out of 20 tosses, it doesn't matter what the other possible outcomes of your test could have been and what you would have inferred in those circumstances. Now, it's not to say the Bayesian doesn't care about long-run properties of tests. They do when they're choosing experiments. Clinical trial experimenters care about properties of tests. But the point is, when it comes to inference itself, after you've actually got an outcome, only the outcome matters for the Bayesian, right? And if you have the same outcome, you make the same inference. It's not dependent on the test. Okay, so last reflection on that stuff. So what are the challenges? Well, I mean, there's sort of different ways of trying to get at the difference between these two approaches. One concentrating on the long-run properties of your inference procedure, and one concentrating on inference in a single case, right? And people dispute what's more valuable. The nice thing about concentrating on long-run properties of an inference procedure is that your the properties of the procedure can then be objective, right? If this procedure is followed many times, there is an objective error probability for your inference given if the hypothesis is true and if the hypothesis is false. So you get objective features of these tests. That seems a good thing for the classical method. Inference is always sort of mediated in terms of objective long-run features of your inference method. But, you know, most cases we actually not so interested in the long run. We actually want to make the best guess we can in a particular case. And the Bayesian claims to have an answer to that problem, also gives output to inference problems that mesh well with our decision-making needs, right? We tend to have to make decisions in single cases. Now, that's sort of just the general difference, but where does some particular sticky issues come up for both of these accounts? Well, the Bayesians always criticize the classical statisticians and their reliance on procedures with examples where experiments are suddenly interrupted. It happens quite a lot in medical trials, right? So we'll have had a plan for a test for a drug, but suddenly they'll pull the plug when certain types of side effects that were unforeseen are revealed, right? Often tests are stopped prematurely for unforeseen reasons. Then it's very hard to work out what in fact the test was, right? What procedure was being followed? What were the possible outcomes of this test, given that we just pulled the plug at a certain time when we noticed some bad side effects? So this is always considered a problem for the classical statisticians. You know, what do we do? Do we have to throw away data when it becomes ambiguous what procedure was being followed? Now, they can have a certain response to that, I think. I won't go into it. It's at least a prima facie problem. For the Bayesian, there's also sort of a challenge, and that's that sometimes it does seem that the long-run properties of a test are important, right? Especially when you think of orchestrated tests where let's say, we're going to toss the coin up to 10,000 times until we get, and we'll stop any time we seem to have evidence favoring that the coin's fair, because that's kind of important to us. We needed to prove to someone that this was a fair coin and we weren't trying to rip them off, right? And so you say, okay, we'll do a test. We'll toss the coin up to 10,000 times, but I'll stop any time the evidence is such that the coin is fair. Right? Now, they might be a bit suspicious of that test. It looks a bit odd that you can choose a test that might have an error probability that favors your needs, right? The classical statistician will say, yes, well, any evidence you get from that test is not as good as evidence you'd get from a different test, so you shouldn't have as much confidence in H. The test matters, right? How you got to this evidence matters. Whereas the Bayesian says, this is a slightly counterintuitive case, but actually still the test doesn't matter. Even if someone's desperately trying to disprove a hypothesis and chooses a test that has a better chance of doing so, that doesn't matter, right? We need to, ultimately, it's only the outcome that matters. Now, this is something I've looked at in past work, and I've sort of talked myself into the fact that actually the Bayesian doesn't have a problem after all, because my general sympathies are with the Bayesian approach to inference, partly because of its neat relation, its elegance and neat relationship with decision making, which is also important to me. But now I want to consider a new challenge, which I think also, in a way, makes the classical approach look better, and see whether this is sort of further reason to reconsider the difference between classical and Bayesian and their relative merits, right? This use-novelty business. So that's just going on in the background. I mean, the general project, the general issue that I'm interested in is the relative merits of this classical versus Bayesian, as construed in the terms that I just construed them. So this use-novelty debate, right? So we're shifting foot a bit now. It's a debate that's been going on in the philosophy of science literature. In that literature, they tend to sort of look at patterns of reasoning in the history of science and try to explain these patterns of reasoning and try to make our formal or logical notions of confirmation match up with the practice of actual scientists. Right? So the types of ideas and beliefs in the scientific community at various times are taken very seriously and are considered to be serious constraints on any kind of formal notion we give of confirmation. Right? So this is a common intuition that people have, right, that have had, and it seems to be a common intuition in science, and that is that confirmation of a hypothesis given evidence depends on whether or not E is use-novel. Depends on, use-novel just means if it's not use-novel, the evidence was in a way used to construct the theory, or the theory was accommodated around the evidence, right? Versus when the theory just makes a prediction, it's something that we don't already know about the world, and then we go out and see if the prediction is true or not. Right? And the latter, if the theory can predict novel evidence that we weren't already sure about, seems like a more impressive for the theory than then its probabilistic relationship with the evidence that it was already designed to fit. Right. Now, this, just for what it's worth, not very important. That's the way I stated it is weak predictivism, which is just to suggest that there's a difference between use-novel and non-use-novel evidence in terms of how well it confirms a hypothesis. Right? Not that accommodated evidence has no bearing whatsoever on the confidence in the hypothesis. So what motivates this idea, right, that we need to think of this difference? Well, the worry was about basically ad hoc or gerrymandered theories to fit the evidence, and that this would show that fitting the evidence can't be everything, because accommodated theories or ad hoc gerrymandered theories around the evidence would score very well, presumably, with respect to fit with the evidence, right? In the relationship between hypothesis and evidence. So we don't want to say that this evidence sort of confirms these ad hoc theories extremely well. Right? That's what they're trying to prevent. So, I mean, consider an intelligent design theory, right, construed to fit the known fossil record, right? So the intelligent design is sort of, in some respect, there's a designer involved. I think this would be a kind of young Earth creationism type, but there's a designer involved in fixing the way the world is, right? Now, how can they explain the fossil record, which seems to show a transition of species or a gradual evolution of species? Well, you know, there's a way you can explain any of these things. Just may add some extra assumptions about the aesthetic tastes of the designer. You know, they wanted to have this sort of nice sort of mural in the rocks of a transition. You can work out an intelligent design hypothesis that will fit that evidence, right? Compare with evolutionary theory constructed for other reasons, but nonetheless able to predict this fossil record. Maybe doesn't confer as high a probability on the fossil record, but still a reasonably high probability, right? Now, of course, we want to say this is more impressive, right? This theory that's constructed for independent reasons that can then predict the fossil record. The fossil record is a greater tip for evolutionary theory than it is for ID theory that's been constructed around that fossil record. Okay, well that seems reasonable, but it's not clear yet exactly where we want to accommodate this, no, I don't want to use that word again, how we want to build in this intuition into our notion of confirmation, right? It may just be that it's a psychological issue or it's a heuristic that we don't need to actually properly build into our confirmation function. Even so, people have tried to take it very seriously, this difference between accommodated versus predicted or novel evidence, right? Now, the good thing is that it seems to allow us to distinguish ad hoc from respectable theories in terms of the support they get from the same evidence, right? But there's a big question of what exactly is novel evidence versus accommodated evidence. So this is Worrell, who's a big proponent of this idea of use-novelty. But he's concerned about this issue, right? Because he wants confirmation not to be about kind of psychological issues of the experiment, how they came up with the theory, how they sort of found the evidence, that type of thing, right? So in a way, he doesn't have that. He's got a kind of Bayesian intuition that all that should matter is the relationship between hypothesis and evidence, not you know, the discovery process, if you like, procedures and processes. But he still is interested in this use-novelty distinction. But this is just him saying, look, rational support should just be a matter of the relationship between evidence and theory or hypothesis. Now, Worrell does do a nice job in shifting the debate. So he wants to find a way to be able to talk about use-novelty, but without having to introduce sort of data about the process of discovery of the experimenter, right? So basically what he does, is he just reconceptualizes the model structure, or he creates a hierarchy of hypotheses in his model that allows him to talk about use-novelty, but nonetheless we still just have a model of hypotheses and evidence, right? So just as a preview, he introduces this idea of a general theory, right? And specific instances of that theory. And so on. So you might have, for the intelligent design case, you've got, you know, the designer who likes no fossils, the designer who likes fossils of type A, the designer who likes fossils of type B, the designer who likes the fossils that we have, that kind of thing. And just this way of organizing hypotheses in your schema, right, allows you to talk in a certain way about accommodating evidence versus novel evidence. Accommodating evidence basically settles a specific version of a general theory, right, whereas novel evidence goes further and actually tests the general theory, right? So this family structure becomes very important, right? Now, just to compare, I mean, you might think that Bayesian doesn't really need to worry about this stuff anyway, because even if this were the case, so usually confirmation for the Bayesian is just the relationship between these likelihood probabilities for different theories, right? Even if it were the case that, look, the evidence is pretty much close to certainty under the gerrymandered hypothesis, slightly less for general evolutionary theory, right? Let's just say. So we might have to say, according to our notion of confirmation for the Bayesian, which does tend to just be the ratio of those two, that actually the evidence does support ID theory, right? That's okay because we can resort to their prior probabilities, right? So I think many Bayesians would just say that, yep, sometimes evidence does confirm the gerrymandered theory, but that's okay because that has such low plausibility to begin with. We're not going to, in the end, have higher confidence for that theory. I think where Worrell goes further is to say, no, look, that's not quite acceptable yet. We still want to have a way of explaining why the evidence doesn't even provide support for this ID theory, right? So we want to be able to discuss Bayesian notion of confirmation in a way that we don't get this evidence supporting the gerrymandered theory, right? So that's where this family structure becomes important, an important addition for the Bayesian, right? So, I mean, just consider this case. We'll just say general evolutionary theory is just a single theory, with, whereas the ID theory has a free parameter, which may be filled in various ways. Here I've just got 8 ways, right, to do with the fossil record, or the tastes of the designer about the fossil record. Now, even if it's the case that the evidence given this particular theory has probability 1, because the theory was designed around it, whereas for ID theory, let's say the evidence has a mere probability of an 1/8, right? Nonetheless, because there's so many instances of this, let's say they all have equal probability. In fact, the probability of the evidence given the general theory is an 1/8, just because of the way that I set it up here. Right? So even though the evidence given this is 1, because there's all these other cases that confer 0 probability on the evidence, overall, just for my simple case, the probability of the evidence given the general theory is an 1/8, right? So the point is, if we're comparing likelihoods at the appropriate level, so we should be comparing this theory with this theory, not this theory with this theory, right? Then we can restore our intuitions about the confirmation that evidence provides, right? We can restore our intuitions so they map those of the scientist. So we just need to be careful in the way we set up our model and the types of comparisons that we're doing, right? We don't need to introduce extra psychological factors to do with the process by which you arrived at the evidence. It's all, once you have your probability model, which admittedly is a creative process, right, where the scientist sort of lays down their opinions in their probability model. Once you have your probability model, we can just look at the structural relations between propositions and if we compare the right sorts of theories, we can restore our intuitions. Okay, so what? Just to reiterate, what Worrell sort of manages to do, mainly because he only considers very simple cases, is to restore this distinction between use novel and accommodated evidence, and also remain within a framework where confirmation just depends on the relationship between H and E. Right? So confirmation with respect to a particular probability model, we might be comparing two hypotheses, H1 and H2. It just depends on those two hypotheses, the evidence and your background knowledge. Right? So those are the only arguments you need for your confirmation function in the Bayesian case. Right? And because Worrell only considers quite simple deterministic cases, he's able to say that any evidence that's required to calibrate a general theory, so any evidence that you need to settle a specific instance of a general theory, doesn't then confirm this general theory. Right? So the general theory gets no boost out of evidence that's required to settle a general instance of it. Right? So evidence that's used for accommodation, accommodating evidence, used to construct the theory, to construct the specific version of the theory, doesn't confer confidence on the theory, general theory itself. That's his main lesson. And in fact, it does bear out quite well for the simple cases that he considers. Right? So Worrell's point is use novelty is not required for calibrating the general theory. Use novel evidence that hasn't been used to fill in the gaps or details of a theory to fully specify it. Okay, that's all very well for the various deterministic cases that Worrell considers, right? Where you have a theory of light, let's say, and you use your evidence to work out the specific wavelength, right, versus another theory. Using the evidence to work out your specific wavelength helps you settle on a specific version of the light theory, but it doesn't confer any. Once you then get a fit with the evidence, this shouldn't give you further confidence in the general theory. The problem is that this nice tidy story breaks down when calibration is an ongoing process, or once we move to statistical hypotheses that are not so neat and tidy as the ones that Worrell considers. Right? So when you have stochastic relations between hypotheses and evidence, maybe because the theory itself is indeterministic, it might be a hypothesis about random sampling results, it might be a scientific sort of indeterministic hypothesis, or it's a deterministic hypothesis, but the evidence is probabilistic due to measurement error, right? Often modeled as a probability distribution. Or because the theory is deterministic but only an approximation, or is known to only be approximately true, or something like this. Some reason for having a statistical relationship between theory and evidence. So here's an example, just to give a bit of a break in a sense from climate science that Charlotte and I were working on, or looking at the way that sort of some climate scientists were handling confirmation given fit. So the evidence here is time series data for climate, for average global temperature increases, typically. Right, that's the data, and you've got these various competing climate models, and fit with the data is sort of something that we might want to consider, evidently. Right? Now, the problem is, where this notion of calibration or accommodating building the theory to accommodate the evidence comes in is with the aerosol parameter, right? So aerosols are small particles in the atmosphere. In the climate model, the aerosol forcing measures the change in the mean temperature resulting from the concentration of aerosols, right? So there's a fair idea of what carbon dioxide does to average global temperature. Much more uncertainty about what aerosols do, although they're thought to have a cooling effect. But even that's unclear. Some accounts, there's some uncertainty as to whether they have a warming effect, but most of the guesses are that they have a cooling effect on the atmosphere. So for instance, the pollution above China has a cooling effect on the mean global temperature, right? So we should be pleased about that pollution for the time being. So the value of the aerosol parameter is unknown, and it's basically left as a free parameter in these models, right? And you use the data to calibrate the model, the mean temperature data. So you effectively use the data to refine your idea of what's the appropriate aerosol forcing, right? You choose the aerosol forcing that has the best fit with the data, right? So we've got these models. We're using the data to settle one of the parameters in these models, the aerosol forcing. So in a way, we're doing this thing where we're constructing the model around the data, right? And so then there's a question, well, now we've used this data, how can we know how confident we should be in these models given fit with the data, right? Because we've just orchestrated fit with the data. And in fact, the IPCC report has this recommendation that you shouldn't use that data again. So it's in a way vindicating what Worrell was saying about the very simple cases, that if you've used the data to calibrate your model, it can't be used to build confidence in the model, right? So you can't double count the data, that's another way of putting it. Now, that's sort of, you can see why they're saying that, and it's all well and good, right? But we have to remember that for these statistical hypotheses, you're never going to sort of settle on one particular instance and rule out all the others like you can in the deterministic case. However much evidence you get, you can always refine your distribution over these specific cases of the general theory. So we basically should never stop using the evidence to calibrate. It would be weird if we sort of used some of the data to calibrate and then said, right, we're going to settle on that theory, and now we're going to start confirming with the rest of the evidence. The more evidence we have, all the better to choose the best value of the aerosol parameter, right? So we can't have this strict distinction, at least according to Bayesian terms, between evidence that's used to calibrate and evidence that's used to confirm the model. And in fact, this use-novelty or no double counting at this stage, even though Worrell was able to tell a nice story for the simple cases, is just not borne out by Bayesian analysis. Bayesians don't sort of construct theories. They just have a probability model that they've constructed, that they're imagining, right, from the get-go. There's no difference between calibration and confirmation. The process of calibrating is also a process of confirming. Basically, calibrating is confirming these specific instances of a theory versus others, right? And this may, according to probability calculus, however it works out in your model, also confirm the general theory. I mean, it just depends on the probability. So in this case, in the climate case, many climate scientists did report getting more confident in one model versus another once that they've done this aerosol calibration. Basically because, you might put it this way, the average likelihood of the aerosol, of the evidence given, this is the time series average global temperature, given this general model family, or with all the ways the aerosol parameter might be, is greater than the average for this other general model family, right? So if that's the case, which can well happen, so, you know, both of these models are using the data to calibrate their aerosol parameter, but there's fits and there's fits, right? Some fits are better than other fits. And it may be that one model family is able to do a better fit than the other model family, in short, right? So you do get confirmation in the process of calibration. And that's just perfectly reasonable in the Bayesian case. There's this idea of separating calibrating evidence and other evidence just doesn't really make sense for these more complicated cases, right? So this was nice for Worrell, right, because he wanted to respect the intuition in amongst scientists of use-novelty, but also have the kind of Bayesian notion of confirmation. Unfortunately, in the statistical cases, we can't have our cake and eat it too, right? You lose one or the other. Now, this is where I think the classical model selection becomes interesting again, right? So I'm interested in sort of challenges to the Bayesian approach, and that's that we can, in a way, respect use-novelty according to classical methods, and we don't really get a logical relation between H and E. The procedure comes to matter, but we can stipulate these procedures in quite an algorithmic fashion, right? So it might not be so bad. So in short, these are interesting, I think, because there is something to that intuition that's represented in that IPCC quote, right? If you've used evidence to calibrate, there's something. Surely we want different evidence to test our confidence in the model. There's something about that that's very appealing, right? And so that's why we might be interested in other ways of trying to get at our confidence in a model that somehow respects that. Because basically we're worried about overfitting theories to evidence. The Bayesian can't really offer a check against overfitting theories to evidence unless this is just borne out in relationships between propositions in their probability model, right? And in fact, the Bayesian, there's no good reason for the Bayesian to focus on, although Worrell provided a nice story with this separation into general families of theories, the general theory in all of its instances. There's no real reason for the Bayesian to focus, to make certain groupings of theories, right? Really, for the Bayesian, all the action is just the competition of individual hypotheses. And really, you should be able to group these in any way or other. There's no sort of natural grouping, except if you're trying to explain to someone your reasoning, right? But that's just explaining your reasoning. It's not really justifying your reasoning, why you've grouped hypotheses the way that you have. So this notion of families of evidence is families of theories seems interesting and not so well explained in the Bayesian approach. So what do the model selection methods do? And I have to say I'm still in the process of trying to work out how these methods fit into the general scheme of things and what to make of all these debates as to whether some methods are Bayesian versus other methods that can be described as classical. So the first thing that they do is they shift our focus of attention from seeking a true theory at this level, like seeking the true theory, to seeking the theory that has the greatest predictive accuracy given long-run properties of the procedure for theory construction. So they shift the focus from the truth of the theory to how predictively accurate the theory could be, which means it need not perfectly represent the truth. It might just be a good predictor of the truth, right? That's the first thing. Now, the reason why we get a no-ish, I added ish, but let's just say no for this here is because to be able to talk about average predictive accuracy or expected predictive accuracy, these methods have to shift their focus to procedures for theory construction rather than hypotheses or single theories themselves, right? So they basically consider a family as a kind of procedure for constructing a particular hypothesis. What you do is you get some evidence. One procedure would be to take general theory A and find the particular version of general theory A that best fits the evidence, and that's your result of that procedure, that construction procedure. Another procedure would be to take a different family and pick the particular instance that best fits the evidence, right? But focusing on a particular family of theories is, in a way, the procedure that you're using. And we're interested in assessing how good these procedures are, rather than the truth of particular hypotheses. So it's rather a different focus, right? But seems to fit more what we're actually doing, right? We are, in a way, zoning in on a particular family of theories and then picking the one that best fits the evidence. Now, of course, so the classical, the idea is to find the procedure that has the best predictive accuracy. We don't know that because we don't know what the truth is, right? So another component of the method, which is really the inference component, you might say, is to look at estimators of expected predictive accuracy, right? How distant this model is from the true model. That's the predictive accuracy, and now we want an estimator of that based on the evidence, right? Now, I think I have 2 minutes. So I'm going to give you an example of an estimation procedure, and then we'll basically finish. But just to be clear, another example, I was talking about climate model families before and fitting the aerosol parameter, but often people just go back to very simple examples in this literature where, say, one procedure is to look at the linear family of curves, right? Another procedure is look at the full quadratic family of curves. Doesn't matter that this is nested in this, right? They're different procedures, and the procedure is pick the curve in your family that best fits the evidence, right? Where there's some measurement error that means that might not perfectly fit. So different model selection methods provide different estimators for the expected predictive accuracy of a procedure. Right? It's a bit of a mouthful as to what they're doing. Now, these estimators have different long-run properties, unfortunately, depending on the truth of the matter, which is the old classical problem. It'd be nice if we could choose the estimator with the best long-run properties, but we're not sure what that is because we're not sure what the truth is. Here's an example of an estimator, which is the one that I think best respects this use-novelty condition, right? And this is called cross-validation. Basically, you get your data, and you're using your data to work out what we think might be the predictive accuracy of this procedure, right? So what you do is you take one data points in the data, use your procedure to get a hypothesis. If it's the linear family, find the best line that fits the data, and then see how well it predicts the last point, right? And do this for all the possible cuts of the data and find the average predictive accuracy you get, right? And this average predictive accuracy is your assessment or your estimate of the performance of the procedure as a whole in terms of predictive accuracy. Okay, now I'm just going to jump to the conclusion because I need to finish. So, with respect to this use-novelty condition, in complex cases, we cannot easily have our cake and eat it too, right? We can't both respect this use-novelty condition, perhaps the way Worrell spelled it out, data that's used for calibration can't be used for confirmation, right? And also have confirmation as just concerning hypothesis and evidence, right? So we can't have both of those things together. So what do we want to give up? I mean, do we want to stay on this side, basically, or this side? Well, I want to suggest I think there's serious reason to take this stuff seriously, right? Because it seems to respect the practices that we actually follow. For cases where we really do follow a procedure to construct a hypothesis based on evidence, it seems more reasonable to assess the expected accuracy of the procedure of hypothesis construction, right? But just as a final note as to whether this is a kind of Bayesian classical divide, and that I think is the real interest. Are these model selection methods distinctly classical, and do they solve a problem Bayesian methods can't solve, right? That's the key question. But one route you might try to explore, which I'd be interested in exploring, is whether actually classical model selection methods, or what are known as classical, just change, in the first instance, they just change the goal or the hypotheses that we're deliberating. Instead of deliberating particular theories, the hypotheses now concern the predictive accuracy of a procedure, right? And then we can still use our Bayesian inference, but with different hypotheses. So maybe, the point is, maybe it's not this Bayesian classical divide in terms of inference, but rather getting the Bayesian to reassess the hypotheses that they're considering in different contexts, and that maybe sometimes hypotheses relating to procedures may be more appropriate than hypotheses relating to particular theories of the world, right? That's it, thanks.
Thank you very much, Katie. So now we'll take questions.
I mean, this is all true, but there's always the practical problem remaining. I think that you can just lie. If the data is public, you can say, I selected this from a singleton set of hypotheses, and it just happens to deterministically predict everything we've seen. So if you really want to apply this to, there's some pseudoscientists you hate, and you want to prove them wrong. You really have to beat out of them what the set of hypotheses was from which they selected the one they actually managed.
Yeah.
And I think, so there's an enforcement issue there, which is it's difficult, like, because you can almost just lie.
Yeah, I mean, so in general, this is a kind of complaint that the Bayesians make against classical statisticians. In particular, because the complaint against the Bayesians is like, well, you guys introduce this subjective stuff. It's all in the head of the experimenter. We stick to objective details. But
I think this is a problem for everybody.
Well, the Bayesian just has quite a different approach.
Imagine I'm a Bayesian intelligent design So
Yeah.
I use a Bayesian method to estimate the best parameters, and then I just select them. And now I redesign my theory and say, actually, it was just deterministically selected all of these type of parameters. And alpha was just equal 0.413 from the beginning. So there is no selection. So I'm not weighed down by this prior probability. And now look how well I perform.
Yeah, I mean, if you take your prior probability to be the whole probability model, the Bayesian, obviously has leeway in terms of what probabilities they specify, what relationships between hypotheses and evidence, and initial probabilities for hypotheses, and so on, right? So in that sense, the Bayesian does have a lot of room to maneuver. And is why Bayesianism is accused of being subjective. But the interesting thing, I think, is the point you brought up earlier. This is the sense in which also the classical statistician is also subjective, because inference depends on the procedure that they're using, but they can always fudge the procedure, right, or lie about the procedure. It's like, oh no, I was always intending to stop at 6 heads out of 20 tosses. I was always intending just to do 20 tosses of the coin. Nothing about this evidence favoring the hypothesis that I wanted to turn out to be better confirmed, right? So they can fudge things at that level, so they do have a lot of leeway. I think, though, they can just, the way to get around that is that they do have to just be explicit about what method they're using. The problem with these gerrymandered in the model selection case, I think, is that estimators turn out to be poor estimators in the long run. So there is a way.
Sure.
There are sort of ways you can respond to this case of the, I've got high confidence in my model because according to my gerrymandered procedure, this procedure has high predictive accuracy, right? In the end, we want to know the real predictive accuracy of this procedure, and so we may have good reason to regard the estimator as being having poor long-run properties in those gerrymandered cases.
Well, if you know that it's gerrymandered, but maybe it's not labeled.
Yeah.
Other questions? Janelle?
Well, can you briefly explain the Bayesian objection to the, let's say, my hypothesis is that bright lights keep crocodiles away.
Mm-hmm.
So we have received evidence for that hypothesis. There are bright lights, no crocodiles.
Yeah. Yeah, I mean, this is one of those classic paradoxes in confirmation theory.
Yeah.
And there is, I don't have at my fingertips what the Bayesian response is. So absences as evidence of a lack of a relation or something. I think what the Bayesian ends up saying is, well, it's going to depend on all the possibilities that you're entertaining in the world, and there may well be some small confirmation that bright lights keep crocodiles away from the fact that there's no crocodiles here, right? But it might only be a small amount of confirmation, given the way things turn.
IGA Good wrote a paper that says exactly that.
Right, yeah. There's a bit of confirmation, just a small amount though.
Okay.
Given all the other possible ways that there may be no crocodiles in this room that don't have to do with bright lights. Right?
Okay.
Yeah. The evidence is also quite likely under the negation of H, right? Which is why you don't get much confirmation, but you might still get a little bit.
Okay.
Yeah.
Yes, Danielle.
I'd like to know if your opinion it makes sense to distinguish between classical model selection, the original Fisherian methods of the significant testing with from classical quality testing with the modern person, because they have two very different approaches towards the management of evidence. First case, we use evidence for statistical inferences, so maybe there are some overlaps with the Bayesian point of view. original column can, I don't know if it can be divided in two parts, because there are, at least from an epistemological point of view, very different views on, I think, on model selection in classical positive testing. Now these two perspectives are merged, but maybe it can be something that can be useful for your analysis. So use of new evidence. So Fisher and the non-person, they have very different approaches to evidence. And okay, now they are considered very important from the fragmentist perspective, but maybe I think that their opinion can be useful for your framework, because there are some Fisherian aspects that surprisingly are more in accordance with Bayesian perspective. I don't know if you have think about it.
So I mean, there might be some divisions in here too, and
Yeah, no, just in addition to the
you're just
classical
thinking
model. Because, for instance, for Fisher, use evidence just for make statistical inferences.
Yeah, although for Fisher's, I mean, in the very simple cases,
Yeah.
Fisher's, it's still mediated by the test that you're
Yeah,
performing.
still, but even for it's interested in the result of one test, while for the other perspective, and it's also a classical one, you are interested in the long run of the experiments, the serious experiments. So I think that this
There's some
partly
room to-
can affect your framework, so you can provide finer grain analysis of this. It's just maybe a suggestion.
Yeah, yeah.
It's not a real question.
It's an interesting thought. Yeah, yeah.
Because we use Fisher, usually it's significant testing when we want to deal with statistical inferences. When we want to make decisions, usually we use classical hypothesis testing made by persons and Neumann.
Right,
So-
they couch their inferences more as
So
decisions.
your picture can be complete, I think, in this way.
Yeah. Well, to be honest, I'm not really up to that kind of. I'm sort of still grappling with whether we might still turn this into take the focus off model selections being necessarily classical and think of it in terms of a change in the way we conceive hypotheses that we're interested in,
Yes.
right? So I'm at a more preliminary level, I think, in terms of sort of giving a taxonomy of the way to think about model selection methods. But I agree, there's going to be just differences between these different camps, and maybe that's an important one.
Other questions?
Yeah.
Well, I just had a comment, which is that I really like your in your opening slides, this way you were distinguishing between classical and Bayesian point of view, I guess. But it also reminded me that it really conflicted with what's considered classical and Bayesian and statistical machine learning, where they have done exactly what you just said. They've really incorporated model selection as a very crucial part of what it means to be Bayesian.
Right.
So the most hardcore people
Yeah.
they always have an error model, for example. So they're always specifying what other evidence could have been created.
Right.
It's
Yeah.
interesting that it
Yeah. Yeah. So I mean, the discussion in model selection, I think, is very confusing. You sort of lose the sense of how Bayesian and classical are being characterized. People seem to just choose the labels as they sort of want to defend, given their background or something. But so I mean, in general, Bayesians should be able to assess long-run phenomena, and you know, we saw with Matthias's talk. I mean, Bayesians can also entertain estimators and consider what their expected accuracy will be. So similarly here, I mean, the Bayesian should be able to entertain the expected accuracy of a procedure. So yeah, so this it shouldn't be so hard to accommodate this type of phenomena in Bayesian reasoning. Yeah, but the inference procedure still differs. Even if we change the hypothesis, the type of hypotheses we're considering, the difference in inference, I think, still remains, whether inference is based on long-run error properties of your mode of inference or whether it's based on your kind of ideas about the single case. Yeah. Thanks.
All right, let's thank Dr. Steele once again.